Hey guys, in this video segment we're going to talk about Dalton's law of partial pressure. So we've talked about a lot of different gas laws coming into this video, and one of the pieces that we did in lab and that we need to kind of address here is what happens when we have a mixture of gases and how do they contribute to the total pressure of that system. So Dalton is a person that we've talked about before, John Dalton. Remember, he came up with one of those first theories of the atom, and one of the laws that he proposed and that we use today is that if you have a mixture of gases in a system, that those individual gases don't really affect each other. Okay, so this law might seem pretty simple at first glance, just saying that the pressure total of some sort of system is equal to taking the pressure of each individual piece and adding them up. Okay, and that, it's a pretty simple equation, pretty simple work there. However, his work, what it showed us was that if you have oxygen in a container mixed with nitrogen, mixed with hydrogen, that the oxygen, the hydrogen, and the nitrogen don't affect each other. They don't mess with each other. They don't change each other. They're just there flying around separate from each other. Okay? So what it's telling us is there isn't anything weird going on, that you can just add up the pressures of each individual gas, and that will give you the pressure total of that gas. Okay? So that's Dalton's law of partial pressure. So let's kind of take a look at what that kind of means by that. So if we take a look here, if we have a container that contains 2.4 atmospheres of hydrogen gas, basically a half a mole of hydrogen gas flying around, and if we have a container that contains 6 atmospheres of pressure of helium gas, or 1.25 moles of helium gas, okay? If we take this container and mix them together or put them together, what we would get was this. So you would still get, if you notice, the same volume. So we're not changing the volume here. However, the pressure would go up to 8.4 atmospheres. So if you take the pressure of the hydrogen plus the pressure of the helium, that gives us the pressure of the total system if we keep the temperature and volume the same, obviously. Okay, so the amount of moles of gas we have in here now would be the 1.75 moles of those gases there. Okay, so let's just do kind of a quick practice problem down here. Our atmosphere is composed of 20% oxygen, 79% nitrogen, and 1% other gases. If the total atmospheric pressure is 760 millimeters of mercury, how many millimeters of mercury pressure does each component contribute to the total? Okay, so in this scenario, what we want to do is, since we have percentages here, what we want to do is break them down and figure out, well, what is each individual? Okay, so don't make this harder than it is. Okay, so we have a total of 760 millimeters of mercury. And we know that 20% is oxygen, so we're going to take that times the 0.2 for 20%, and then we're going to do the same thing times the 0.79 for our nitrogen. So this is our oxygen, this is our nitrogen, and then of course take that same value, the 760, times the 0.01 for our other gases. Okay, and if we do that, we should be able to get to an answer here. Okay, so all we really have to do is take the 760 times the 0.2, the 0.79, and the 0.1, and if we do that, we'll figure out the different percentages of each one of those gases. Okay, so doing that, if we do 760 times 0.2, we end up with 152 millimeters of mercury. And nitrogen, you take the 760 times 0.79, we get 600.4. We're dealing with just a couple of 600 sig figs here, so we'll just call that 600. And then obviously the 760 times the 0.01, and we get about 7.6 there. So we get 152 millimeters of mercury of oxygen. We get about 600 millimeters of mercury of the nitrogen, and we get about 7.6 millimeters of mercury for our other gases here. Okay, alright, so that's just one way this problem can be solved. There are additional practice problems for Dalton's law in worksheet number 2.